This video is a graphic representation of what I believe is occurring in the process of catalyzed nuclear fusion, historically referred to as cold fusion and more recently as low-energy nuclear reaction. This reaction was originally observed by Martin Fleischmann and Stanley Pons, who reported an anomalous generation of heat in an experiment in 1989 in which palladium was used as a cathode for the electrolysis of heavy water. While there were initial difficulties in replication of the experiment, subsequent attempts have shown a positive correlation of heat and helium production, indicative of nuclear fusion but without the gamma ray emissions associated with high energy fusion. The original null results are now attributed to a lengthy time frame required for loading the palladium catalyst with hydrogen. This was initially unrecognized as a parameter of the experiment. Palladium in lattice form takes the shape of a face-centered cubic crystal, as shown here in this unit cell. The blue nodes represent the atomic nuclei of the palladium. The center of the cube forms an octahedral space with the face-centered nodes. The center of the octahedral space does not contain any atomic nuclei of the lattice element, but it can admit other atoms. In particular, it readily absorbs hydrogen as hydride at room temperature. The space along each edge of the cube between the vertex nuclei and the two adjacent face-center nodes, of which there are 12 instances, one for each cubic edge, constitutes 1/4 of an octagonal space formed with 3 adjacent cells, so that for each cell in the lattice interior there are 4 octagonal spaces. In the interior of the lattice there are 4 nuclei that can be uniquely assigned to each cell. For example, here we have 1 vertex and the 3 adjacent center nodes. Thus there are an equal number of palladium atoms in octagonal voids or chambers in the extended structure, which I'll be referring to by the initial O. The palladium can absorb approximately 900 times its volume of hydrogen at room temperature, which is equivalent to occupation of a bit over 70% of the O chambers, assuming 1 monatomic hydrogen atom per chamber. Here the red spheres represent hydrogen, 1 in the center chamber and 2 at random locations in chambers shared with other cells. It should be noted that the cell represented here is not a discrete unit of the lattice, but is rather a division made for analytical purposes. The Coulomb force, broadly understood to include all electromagnetic interactions, is responsible for bonding of the individual atoms in the lattice. It is at work and play between the blue and nuclear nodes and between them and any absorbed red atoms, and is generally dealt with by mathematical modeling of the wave function, psi, to describe the interactions. Here representative interactions are shown, but there is held to be just 1 wave function for the whole system. This toy model represents the same face-centered structure, but here we've substituted equal-sized spheres centered on the same nodes as the nuclei of the last slide. They represent the extent of the covalent bond of the lattice atoms. Palladium has a covalent radius of 139 picometers, and nickel's is 124 picometers. Here we have removed the left-hand side of the unit cell, consisting of 5 atoms, and twisted the structure approximately 60 degrees counterclockwise to reveal the interior of the O chamber. We've also added the 4 face-centered atoms on the far side of the right-hand side of the cell, 2 of which are visible here. The 5 nodes of the right-hand face in the first representation of the unit cell are indicated here. Note that in addition to the O chamber where the hydride is located, there is a triangular opening at the top right, which we will call a tetrahedral aperture, and which leads to a tetrahedral chamber, T, formed by the front upper 3 spheres and the now central sphere which occupies a face-centered node on the original right-hand face. In the interior of the lattice, around each sphere, there are 12 identical spheres. While it is perhaps not apparent in the last slide of the face-centered cube, each face-centered node constitutes a vertex node for another interlocking set of unit cells, one of which is shown here, so that every sphere not on the exterior layer of the lattice is similarly surrounded by 12 spheres. In addition to the three orthogonal directions of the face-centered lattice, in the above cube octahedron, there are 4 axes of symmetry that correspond with a tetrahedral configuration, with its origin at each sphere, and in which the 4 centered nodes, as on the front left above, correspond with the edge midpoints. Therefore, in this view of the same lattice, each of the 12 edges has a node at its midpoint around a sphere centered at the center, and the 4 diagonals radiate through the T apertures. Therefore, in addition to 4 O chambers of the unit cell, 3 halves on the 6 faces, 8 eighths on the 8 vertices, there are 8 T chambers. In the interior extent of the lattice, each of the 8 T chambers leads from an O directly toward the center of the 8 nodes represented by the vertices of the face-centered cubic. Returning to our original face-centered cubic, in the interior extent of the lattice, each of the 8 T chambers leads from an O directly toward the center of the 8 nodes represented by the vertices of the face-centered cubic. Here we have a direct view of an O chamber. Here we have a direct view of a T aperture with the T chamber behind. Here we have a depiction of the 4d10 valence electron orbitals and their relationship to the covalent bonding of the lattice atoms and the absorbed hydrogen. Here we have another view of the face-centered cubic lattice, which gives an idea of the porosity of the surface when it is in a rectilinear configuration. Here we have another view of the same lattice, but with the packing sheared along the planes normal to the tetrahedral axes. This forms an octahedron and shows the tightness of the surface in such configuration. The O chambers still reside in the interior, but the surface has less than 20% the porosity of the last photo, due to the exclusivity of the T apertures. Here is a view of a surface of the lattice as determined by the cubic configuration. The interstitial chambers are loaded with hydrogen. The elements are drawn to scale. The lower right shows the presence of 2 atoms in a chamber, as might occur with the application of energy of electrolysis. The gap of the O chambers, measured left to right and top to bottom, determined by the covalent radii of the lattice element, is 115.2 picometers for palladium and 102.7 picometers for the nickel lattice. The red dots represent hydrogen, which has a covalent radius of 31 picometers or a diameter of 62. Deuterium is reported to have a slightly smaller covalent radius than protium, but still within the stated uncertainty. It is assumed that the hydrogen moves in the chambers, fluctuating between covalent bonding with the lattice and ionic interaction in the presence of additional hydride, as at the lower right. The orange ellipsoid at the lower left represents an atom that is entering a tetrahedral aperture due to electrolytic loading. As it enters and gets closer to the surrounding 3 lattice atoms, the two to either side and the one beneath it. Coulomb forces attract the positively charged proton of the nucleus toward the interior of the T chamber. This elongates the atom so that it can fit between the valence shells of the three atoms forming the aperture. In the case of ideal palladium, the aperture will admit a sphere of 43 picometers diameter, and the nickel a sphere of 38.2 picometers diameter. Note that the only way to fill the interior O chambers with hydrogen is by tunneling through the T apertures and chambers. Here the result of that effect is indicated by the dotted hydrogen atoms in the next layer down. The lattice will expand slightly during the absorption process. A close-up of the T aperture with the plane of the three defining atoms in the plane of the screen. The nuclei at the lattice nodes are represented as blue dots, not to scale. The fourth atom of the tetrahedron is centered in the rear. This shows the symmetry of the entry and its relationship to the electrostatic attraction of the opposing atom. The red sphere at the center, behind the elongated atom passing through the aperture, is a snugly fitting hydrogen atom. One is shown to the side for size comparison based on the covalent radii of palladium and hydrogen. Another view of the tetrahedral configuration with three of the atoms resting on a plane at bottom. Yet another view with two of the four planes of the tetrahedron perpendicular to the viewing screen. Note the elongation extent of the hydrogen on entering the chamber from the bottom, representing charge distribution in the atom. The tetrahedral chamber is the nuclear reactor chamber of the palladium hydride lattice. While the octahedral chamber is well recognized in the extant literature in connection with such lattice hydrides, and the tetrahedral requirement for tessellation of a lattice with an octahedral component is known in geometric circles, I have found no reference to its significance in the literature to this process. In the case of the Palladian lattice, the T chambers will hold a sphere of 62.5 picometers diameter, which is a little less than a picometer larger than the hydrogen diameter of 62 picometers based on the covalent radius. In the case of nickel, the spherical diameter fit is 55.7 picometers. Therefore, in the case of palladium in particular, the chamber is a snug fit for the hydrogen atom, and we would anticipate it remaining there unless deeper interior vacancies allow and continued electrolytic and other atomic pressures force it into an adjacent O chamber. In such case, we would anticipate the ellipsoid of the last frame to find its way to the right into the empty central bottom O chamber beneath the top sphere. Where the lattice has reached its absorption capacity, the hydrogen will remain in the T chamber, with its nucleus centered by the valence constraints of the lattice in the crosshairs of the central axis of each of the four adjacent apertures, as in the previous slide. We would expect that continued packing of the externally applied energy would result in entry of additional hydrides here. As well as simultaneous entry of two atoms, as at the central left partial O, upper right aperture. In these cases, with some probability, we would expect the nuclei to fuse at the chamber's center, releasing spin energy to the lattice as heat. In either case, we can see potential for events of electron capture by the proton entering or the one already positioned at the center. And in the case of deuterium, for the shielding of the protons by the neutron of each atom as the nuclei approach the center. Note that the tetrahedral configuration of the chamber is conducive to the tetrahedral arrangement of the helium nucleus. Helium fusion products are represented in magenta. The covalent radius of the helium-4 is slightly smaller than that of hydrogen at 28 picometers, for a diameter of 56 picometers, compared to the spherical capacity of the T chamber of nickel at 55.7. Heat from fusion would result in phononic and other lattice energy with a release of the helium from the T chamber. If this process is naturally efficient, the fusion will take place at the earliest opportunity as new atoms are absorbed and enter the outer layers of T chambers. The deeper atoms in the filled O chambers maintain electrostatic pressure, which aids in securing atoms in the outer T chambers against movement with the entrance of fusing components. Palladium and hydrogen have the same electron negativity of 2.2 on the Pauling scale. This indicates that the nuclei of the bonding atoms will be equidistant from the covalent bonding electrons. Assuming the covalent radius of the palladium atom is the determining factor in this coupling, due to the Pauli exclusionary principle, and the fact that neither the hydrogen nucleus nor electron can be found within the regions represented by the interior of the spheres of our cuboctahedral lattice, there are only 4 regions from any given palladium atom in any given O chamber where the covalent bonded hydrogen nucleus can locate, and that's in the region of the tetrahedral apertures. In fact, since the hydrogen nucleus must locate a distance equal to the palladium covalent radius from the bonding electrons, the position for the nucleus is precisely in the center of the aperture and throat, i.e. the point of maximum constriction in the plane of the 3 defining lattice atoms, nuclei. The position is shown at H in the view from the XY plane and from the YZ plane here. The position at HI to the left of H is that of a hydrogen atom with nucleus not shown to scale, that is not in a covalent bond, but is centered in the tetrahedral chamber. If a covalent bond is formed with a palladium atom to the left of HI, the parameters of the Pauling scale dictate that it has but one place to go. And that is through the T aperture where H is centered toward the position indicated by the HI prime. The path is shown in cyan in both views and is through the position of the first hydrogen nucleus. This represents a second avenue for fusion, one we might imagine to be more energetic. In the process, the covalent bonds are broken, and if both hydrogen are deuterium, then helium-4 is produced. The following is a list of lattice and reactant data used in this development. The following animation of the various lattice interactions is performed without narration. It is my belief that the anomalous heat of the Fleischmann-Pons experiment was due to low-energy fusion, and that its replication problems were due in large part to the unrecognized constraints of the absorption mechanism and saturation requirements as indicated above. In particular, this includes the need for packing of the interior so as to aid in nuclear target confinement and stabilization in the tetrahedral chambers. This latter structure appears to be unrecognized as a principal configuration for the process of cold fusion. It also explains indications that the process tends to occur primarily in the surface areas of the lattice and why helium produced in the lattice bulk tends to remain there. In regards to the T chambers, the high degree of precision in the fit of a covalent hydrogen atom in the interstitial space of the palladium lattice, along with the valence structure and lattice configuration, establishes a reason for the importance of palladium in the LENR process. It also suggests a theoretical guideline in a search for other elements, alloys, and molecules, including organic molecules, and for nanoengineering that might foster the process. This unique palladium configuration comprises palladium electronegativity of 2.20 equal to that of hydrogen deuterium, which centers the hydrogen nucleus of an interstitial covalent bond in the tetrahedral chamber aperture. T-chamber volumetric capacity matched closely to hydrogen covalent radius. No 5s valence orbital except with excitation, thus no covalent bonding potential in the T-chamber absent such excitation. Upon such 5s bonding with palladium, T-chamber geometry that fosters projection of the hydrogen nucleus through the T aperture center. In light of this configuration, it is also easy to understand why there are none of the usual radiation products of the process, as the confluence of nuclear components is primarily a result of a scale geometrical confinement and charge distribution constraint, which does not require high-velocity collision. I hope that those with an interest in this process will take the time to review and elaborate on this development. It is my belief that LENR is real and that this geometric analysis forms the basis of a theoretical understanding that will be of benefit for further investigation. The examination of the cuboctahedral interstitial spaces is an elaboration of some non-standard research involving classical discrete wave mechanisms I have been engaged in over the past 2 decades, which can be found on the same YouTube site as this video. Most of the remaining atomic information can be found on Wikipedia and on various governmental and academic sites on the web, notably at chemwiki.ucdavis.edu. I can put the lattice calculations in respectable form if there is sufficient interest, and we'll be happy to do so.